KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss exercise problem numbers 30, 31 and 32. Okay, right. So first we are going to discuss exercise problem number 30. Okay, right. So here first we will see the problem, then we will go for solution, right. So this is what a Cassegrain telescope, which is the reflecting telescope that we discussed in Ray Optics Chapter last class, right. So while seeing this video, you just go through the last class from Ray Optics, okay, last theory class from Ray Optics, okay. So after seeing the telescope, you go through this problem, right. So it is what Cassegrain telescope, which is a reflecting telescope. So this telescope uses reflection as the phenomena, uses two mirrors as shown in the figure, right. So there is one figure in that class, right, I drew on the board when I was explaining that the Cassegrain telescope, that is what reflecting telescope. You just keep that picture in your mind, okay, then you can easily understand this problem, right. Such a telescope is built with the mirrors 20 millimeters apart. Such a telescope is built with the mirrors 20 millimeters apart, full stop. If the radius of curvature of the large mirror is 220 millimeters and small mirror is 140 millimeters, right. Okay. So after that, where will the final image of an object at infinity be? Where will the final image of an object, right, from where will the final image of an object at infinity be? That is what we have to find, okay, right. So here he is asking to find the position of the final image, the position of the final image, that is what like image distance, okay, right. So if you see this problem, you can understand, if you see this problem, you can understand that is what in case of Cassegrain telescope, in case of Cassegrain telescope, you can understand that, right, there are mirrors, that is what to get a reflection of light, to reflect the light there are mirrors, right, there are two mirrors and the telescope is built with the mirrors, right, 20 millimeters apart, it is the distance between the mirrors, and the radius of curvature of the large mirror, there are two mirrors, one is the large, another one is the small. So for the large mirror they have given radius of curvature. You know what is radius of curvature? Radius of curvature is the radius of a sphere in which mirror is a part, in which mirror is a part, right. So radius of curvature of the large mirror is 220 millimeters, right, and the small mirror is 140 millimeters. Now the question is, where will the final image of an object at infinity be? Where will the final image of an object at infinity be? So we want to find, we are going to find the image distance, that is what v, generally we are using small v for image distance and small u for object distance, and small f for focal length. Okay. So this is that what cosmic ray telescope. Next, see here solution. See this one. So first observe carefully. The image formed by the larger mirror acts as a virtual object for the smaller mirror, right? So there are two mirrors. One is the concave mirror, which is the larger in size, and another one is convex mirror, which is the smaller in size. Okay. Here the image formed by the larger mirror acts as a virtual object for the smaller mirror. This is the working of telescope. This point is from the working of telescope, full stop. Parallel rays coming from the object at infinity. Parallel rays coming from the object at infinity will focus at 110 millimeters from the larger mirror, right? Parallel rays coming from the object. Parallel rays coming from the object at infinity will focus at 110 millimeters from the larger mirror. Because of this, this is what they have given now. It is what 110 millimeters, right? It is what 140 millimeters, and it is what 210 millimeters, right? These are the given things. Okay, right? So what he is saying is parallel rays coming from the object at infinity will focus at 110 millimeters from the larger mirror. You know the relation between radius of curvature and focal length, right? It is what r is equal to 2f. R is equal to 2 into capital R is equal to 2 into small f generally, right? Okay. So f is equal to r by 2, no? So that is what 220 by 2 is 110 millimeters. You know that what is meant by focus, right? Focus is a point where the rays will meet to form an image. To form an image, okay? That is what parallel rays coming from the object at infinity will focus at 110 millimeters from the larger mirror. Just we took this value, that is what radius of curvature r is equal to 2 into small f, right? Next, the distance of the virtual object for the smaller mirror. The distance of the virtual object for the smaller mirror is 110 minus 20 is equal to 90 millimeters. 110 minus 20 is equal to 90 millimeters. You know that is what these two mirrors are separated by. These two mirrors are separated by 20 millimeters, no, right? So that where the virtual object from the smaller mirror means this 120 minus 20, sorry, this 110, it is 110 more, sorry, this is also 110. 110 minus 20. 110 minus 20 means it is 90 millimeters. 90 millimeters is the distance of the virtual object for the smaller mirror. For the smaller mirror, right? Now, for the small convex mirror, we have u is equal to minus 90 millimeters, comma f is equal to minus 70 millimeters. Minus 70 millimeters, because you see this one, for smaller mirror radius of curvature is 140 mm, no? Then what about focal length? R by 2, no? It is what 70, including sign convention, minus 70 millimeters. Okay, right? V is equal to question mark. V is equal to question mark. Using mirror formula, that is what 1 by V is equal to 1 by F minus 1 by U. 1 by V is equal to 1 by F minus 1 by U, that is equal to 1 by minus 70 minus of 1 by minus 90. So minus, it is minus plus now here. So 1 by minus 70 plus 1 by 90. So if you do this calculation, you will get it as 1 by 315. 1 by 315. So 1 by V is equal to, it is what minus 1 by 315 now. When 1 by V is equal to minus 1 by 315, what about that V value, which is minus 315 millimeters, right? So anyhow, the values what we are taking in millimeters now. So here also millimeters, here also, everywhere is here millimeters. That's why the answer also will be in millimeters. V is equal to minus 315 millimeters. Thus, the image is formed at 315 millimeters from the smaller mirror. So, 315 is the answer. 315 millimeters is the answer where the final image of an object at infinity B. Okay, right. Next problem, that is what next exercise problem. That is what 31. See here. First, I will tell you the problem, then we will go for solution. See here. Light incident normally on plane mirror attached to a galvanometer coil retraces backward, right? Light incident normally on a plane mirror attached to a galvanometer coil retraces backward as shown, right? A current in the coil produces a deflection of 3.5 degrees from the mirror. 3.5 degrees from the mirror. What is the displacement of the reflected spot of light? What is the displacement of the reflected spot of light on a screen placed at 1.5 meters away? On a screen placed at 1.5 meters away, right? So, observe carefully. So, understanding problem is very important for us, right? So, if you understood the problem, right? If you understood the problem, it is very important for us to understand the solution, okay? Right. Light incident normally on plane mirror attached to a galvanometer coil retraces backward as shown. A current in the coil produces a deflection of 3.5 degrees of the mirror. 3.5 degrees of the mirror. What is the displacement of the reflected spot? What is the displacement of the reflected spot of light on a screen placed 1.5 meters away? 1.5 meters away. Okay, right. So, now we are going to see the solution. You see this picture also now, right? So, that is what when the mirror is going to rotate theta, what happens to the light ray which is going to reflect it? 2 theta, that's you know. So, that only he is saying once again here, that is what when the mirror is turned through angle theta, when the mirror is turned through angle theta from position m to m dash, when it is theta, this is also theta, no? It is what you just see geometrical mathematics, right? So, according to the geometrical mathematics, when it is theta, this is also theta, right? So, when the mirror is turned through angle theta from position m to m dash, comma, the reflected ray turns through an angle 2 theta. It is the condition followed by plane mirror regarding the reflection of light. Okay, it is already there when we discussed about, that is what the reflection phenomena, and when we discussed about the reflection of light in case of plane mirror, we got it. When the mirror is going to turn through an angle theta, the reflected ray turns through an angle 2 theta, right? So, this is the condition satisfied by a plane mirror regarding the reflection of light. See here. So that the reflected spot moves, right, from P to Q, that is what position P to Q, and angle POQ, this is P, it is Q, and it is what O, right? POQ, it is what O, right? You just take it as this point as O, right? It is what POQ is equal to 2 theta. You know, theta they have given, it is what 3.5 degrees. 3.5 degrees, right? So, when it is 3.5 degrees, right? When it is 3.5 degrees, 2 theta is equal to 2 into 3.5, which is 7 degrees, right? Now, tan theta is equal, this is what tan 2 theta. Tan 2 theta is equal to d by 1.5. No, you know that the formula for tan theta is opposite side by adjacent side. Opposite side by adjacent side. So that d by 1.5. D by 1.5, right. Therefore, displacement of the reflected spot on the screen, displacement of the reflected spot on the screen is small d is equal to, from this formula, we are not doing anything here, just we are going to find d value, right? So from this, d is equal to 1.5 tan 2 theta. So 2 theta means 7 degrees, 1.5 tan 7 degrees, that is equal to 1.5 into 0.1228. It is the value of tan 7 degrees. So if you multiply these two, you will get it as 0.1842 meters. 0.1842 meters, right? So when it is 0.1842 meters, and if you want to write, suppose if you write in centimeters, you will get like this. That is what, right? That is what 18.4 centimeters. 18.4 centimeters, right? So 1.5 into 0.1228 will give us 0.1842 in meters, because this is what 1.5 we are taking in meters now, so that the answer will be in meters. But if you want, you can convert into centimeters. That is what 18.4 centimeters. Just you write in place of meter, you write 100 centimeters, right? So that because of due to the mathematical process calculation, you will get it as 18.4 centimeters. 18.4 centimeters. Okay, right. Now we are going to see the next problem. That is what problem number 32. Next exercise problem 32. Okay, see here. The figure, see here. So first I will go through the problem, then solution. See this. Figure shows, this is what the figure, right? Figure shows an equiconvex lens. Figure shows an equiconvex lens, right? Figure shows an equiconvex lens, right? That is what the refractive index 1.5. Refractive index 1.5. In contact with a liquid layer. In contact with a liquid layer on top of a plane mirror. On top of a, try to imagine what's happening in the problem and in the picture, to imagine. That is very important for us to understand the solution, right? Figure shows an equiconvex lens of refractive index 1.5 in contact with a liquid layer on top of a plane mirror. It is the plane mirror. It is a plane mirror. Okay, right. Full stop. A small needle with its tip on the principal axis is moved along the axis until its inverted image is found at the position of the needle. See here. So it is the small needle now, right? So which is going to move. This is going to move, right? So this is going to move like this and like this. Until there is a inverted image, that is what, like this image in this place of needle, right? So it is also needle, it is the image of the needle. So you have to see like that, right? So you have to move until its inverted image is found at the position of the needle, okay, right, full stop. The distance of the needle from the lens, is measured to be 45 centimeters. The distance of the needle from the lens is measured to be 45 centimeters. Full stop. The liquid is removed, and the experiment is repeated. The liquid is removed and experiment, like the second case. In first case it is okay. In the second case, we are going to remove the liquid and the same experiment will be repeated. Now the new distance is measured to be 30 centimeters. Now before it is 45 centimeters, no. Now it is 30 centimeters. In the presence of liquid, it is 45 centimeters. In the absence of liquid, it is 30 centimeters. Right. What is the refractive index of the liquid? So liquid is a medium, no? So it has its own refractive index. We don't know what type of liquid he kept here. That's why he is asking to find what is the refractive index of the liquid which was here in first case, right? That is the question. Now, you just carefully observe the picture. First, you have to understand the picture, right? This is what is the mirror and what is the liquid, what is the equiconvex lens, right? And what is the needle object, that is what object needle, and what is the image needle, and how the light rays are going, right? So here the refraction takes place, because when a light is entering from one medium to another medium, right? From one medium to another medium, it bends at the point of separation of both the media, no, right? That is what we are calling it as refraction. Okay, so it is what refraction. That's why what I am saying is, you understand the information what they have given in the question along with the picture, okay? So in entire Ray Optics chapter, ray diagrams are that is what the picture what they have given is important to understand the solution, right? So there are two cases, ma. In first case the liquid is present, in the second case liquid is not present, right? When the inverted image present at the position of the needle, there they have given in the presence of liquid it is 45 centimeters and in the absence of liquid it is 30 centimeters. Based on this data given in the question, he is asking to find what is the refractive index of the liquid, right? You know, in first case it is, observe carefully, distance of the needle from the lens. In the first case, distance of the needle, right? See the red light, ma. Distance of the needle from the lens in the first case is equal to focal length f of the combination of convex lens and plano-concave lens. Focal length f of the combination of the convex lens and plano-concave lens formed by the liquid. You know, if you see the shape of the liquid, it is like a plano-concave lens, no? Plano-concave lens, right? So this focal length f of the combination of the convex lens and plano-concave lens formed by the liquid is equal to distance of the needle from the lens in the first case. That is what already given, no? So this distance given. So this combination is equal to 45 centimeters, right? From these two things you can write capital F is equal to 45 centimeters. But you keep in mind, capital F is the combined focal length of convex lens and plano-concave lens. Okay, right. Second case, see here. Distance measured in second case is equal to focal length of the convex lens, because in the second case there is no liquid is absent, we removed the liquid. So distance measured in second case is equal to focal length of the convex lens, that is what f1 is equal to plus 30 centimeters, right? So when it is plus 30 centimeters and when it is 45, it is what combined focal length, right? You can write this relation, no? That is what a combination of focal length. You know, the focal length f2 of the plano-concave lens is given by, you know, this formula 1 by f is equal to 1 by f1 plus 1 by f2, right? f1 theriyumu, a capital F also theriyumu, right? But f2 theriyadu. So from this formula, that is what 1 by f2 is equal to 1 by capital F minus 1 by f1. It is from this, I am not writing newly, right? It is from this. Just I am writing 1 by f2 as a subject to find out the f2, right? So it is 1 by 45 minus 1 by 30. That will be 2 minus 3 by 90, that is equal to minus 1 by 90. So when 1 by f2 is equal to minus 1 by 90, f2 is equal to minus 90 centimeters. f2 is equal to minus 90 centimeters. This is the focal length of the plano-concave lens formed by the liquid. Formed by the liquid. Right. Now, for the equiconvex lens, we have, equiconvex lens means, R1 is equal to R, R2 is equal to also in magnitude R only, but according to the sign convention, it is minus R. And F is equal to 30 centimeters already given, right? And mu is equal to 1.5 already given. From all these things, right, using lens maker's formula, you can find out that 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. Substitute all these values. Then you can find out that capital R is equal to 30 centimeters. Capital R is equal to 30 centimeters, right? It is what capital R is equal to 30 centimeters using lens maker's formula, right? Substituting, this is what F as 30 centimeters and mu as 1.5, and in place of R1 capital R, in place of R2 minus capital R, so that here minus of minus plus will come. So 0.5 into 1 by 2 R, 0.5 into 2 by R, right? So 0.5 into 2 means 1. So you can say that R is equal to 30 centimeters, right? Okay. Next, for plano concave lens, F is equal to, it is what the plano concave lens F is equal to minus 90 centimeters, we got it. For concave surface, if you observe carefully, this part of the convex lens formed this part of, that is what the plano concave lens. It is what plano, it is what concave lens, right? Here we have liquid only, but you see the shape. What is the shape of the liquid? That is what plano concave lens. So by writing F as minus 90 centimeters, right? And for concave surface, R1 is equal to minus R, you know that is minus 30 centimeters. And for plane surface, R2 is equal to infinity. And write down all these values in this formula, that is what 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2, right? So 1 by minus 90, 1 by minus 90, because F is equal to minus 90 is equal to mu minus 1, that is what that we have to find, mu value you have to find, 1 by minus 30 minus 1 by infinity. So that finally you will get it as mu minus 1 is equal to, it is what, 0. Something by 0 is equal to infinity, something by infinity is 0, right? It is what, minus 1 by 30, right? And mu minus 1 is equal to 1 by 3, mu minus 1 is equal to 1 by 3, mu minus 1 is equal to 1 by 3, correct only, but we want to find mu now. So mu is what, 1 plus 1 by 3, 1 plus 1 by 3, right? So when it is 1 plus 1 by 3, that is equal to 1.33, right? It is the refractive index of the liquid what he is asking to find, that is 1.33, okay, right? So in this class, we focused on 3 exercise problems. The first problem number 30 belongs to Cassegrain telescope, which works by using the phenomena of reflection, which is also called as reflecting telescope. There, by giving the radius of curvatures, we found the focal length, right? That is the formula R is equal to F. Afterwards, by substituting in the formula 1 by F, 1 by V is equal to 1 by F minus 1 by U, we found V value, which was minus 315 millimeters. So in the second problem, right, he has given, that is what he is asking to find what is the displacement of the reflected spot of light on a screen placed 1.5 meters away, right? The condition when the mirror is turned through angle theta from position M to M dash, the reflected ray turns through an angle 2 theta, right? So by using that condition, we found tan 2 theta, right? 2 theta we found, then tan 2 theta. By using the formula tan theta is equal to opposite side by adjacent side, we found D as 18.4 centimeters. 18.4 centimeters. Okay. So already we are getting in terms of meters, that we can convert into centimeters. 1 meter is equal to 100 centimeters, right? In the third problem is an important problem. It is the last problem, right? So 32 problem. Here they have given one situation. There we have a plane mirror and a liquid and a equiconvex lens. Equiconvex lens. So based on the given things, he is asking to find what is the refractive index of the liquid. This problem has consisting two cases. One is the presence of liquid, another one is absence of liquid. So with the presence of liquid, you can find the focal length of the combination as 45 centimeters, and then in the second case, right, f1 is equal to plus 30 centimeters. By using that combination of focal length formula, we found that f2 as minus 90 centimeters, that is the focal length of plano concave lens formed by the liquid, right. So by applying lens maker's formula, in one case it is you are getting r, we are getting r value as 30 centimeters, and the second case, right. So by applying the same lens maker's formula, here you can find out that mu value as 1.33, okay. So this is the last class regarding ray optics numericals, right, ray optics numericals, right. So in our coming class, we will come with the numericals from wave optics, okay, right. Thank you.